Hey guys, Mr. McKinney here, just going through our video series on implicit differentiation and related rates. This time we will involve transcendental functions. Whenever you see the word transcendental, we're just referring to the trig functions, the exponential functions, and the logarithmic functions. Basically anything other than the polynomial functions that we cover in this class. Implicit differentiation and related rates was essentially Unit 4. So we're basically redoing Unit 4 in one day. So some of these topics may be going pretty quickly. If you don't understand them, I would go back and watch the Unit 4 videos and see if that helps, because this is all the same topics that we went over in Unit 4. Okay, so when you have implicit differentiation, that's just saying that you can take the derivative without solving for y first. So you can find dy dx or dx dy or dy dt. Like you can take the derivative with respect to whatever variable you want, and you don't have to solve for y first. So if I'm asked to find dy dx, I'm going to be taking the derivative with respect to x. So when I take the derivative of each piece, I need to keep in mind that I'm taking the derivative of them with respect to x. So let's write this equation out again and then use implicit differentiation to find the rate of change of y with respect to x. Okay, so x times y, I'm going to need to use the product rule here. So x times the derivative of y with respect to x, plus, and then y times the derivative of x with respect to x. dx dx is always going to be 1, so you don't have to write that, or you can write it and then just show that it goes to 1. So both of these terms came from x times y. We use the product rule there. The derivative of x is 1, and the derivative of a constant is 0. Now again, instead of writing 1, we could have written dx dx, but that's going to simplify down to 1. So now I'm trying to solve for dy dx. So I need to move everything else over to the other side and then divide by whatever's in front of your dy dx. So I'd get x times dy dx equals, when I move this y and this 1 over to the other side, they're going to become negative y minus 1. And then to get dy dx by itself, I would just divide both sides by x. So the rate of change of y with respect to x would be negative y minus 1 divided by x on this problem. So again, implicit differentiation just refers to the fact that you can find dy dx without solving for y first. This problem you actually could have solved for y and used the quotient rule and gotten the same answer, but it's a lot easier to use implicit differentiation. All right. Oh, one thing I forgot to mention, there's a handout that has all of the examples printed up on them. So if you want to print that handout out, and all the rest of the examples will be on there. If that link is not posted, please email me so I can post that link. Okay. Next one, find dy dx for cosine squared of x plus sine squared of y equals 1. Notice that we have different variables on the inside of each of these. So cosine of x squared, I'm going to rewrite as cosine of x squared plus same thing for the sine squared of y. Sine of y squared equals 1. I have not taken the derivative yet, I've just rewritten it. A lot of students make fewer mistakes if they rewrite this type of function like this. All right, so the derivative of cosine squared, the outside function is something squared, the inside function is cosine. So we're using the chain rule here. So 2 times cosine of x, now it's just to the first power, and then times the derivative of cosine would be negative sine of x, and then the derivative of x would be dx dx. But that can go away. I don't really need to write that. All right, same idea here. So 2 times sine of y, the new exponent is 1, I don't need to write that, times the derivative of sine of y, which is cosine of y, times the derivative of y, which is dy dx. Since we're taking the derivative with respect to x on this problem, then dy dx is going to stay there. dx dx is going to go away because that's 1. And again, when you take the derivative of a constant, you get 0. So now I just need to solve for dy dx. So this could be written, I'll simplify it a little bit first. So negative 2 cosine of x sine of x plus 2 sine of y cosine of y times dy dx equals 0. So to get this term to the other side, since it's negative on the left side, I would add it over to the right side. So 2 sine of y cosine of y dy dx equals positive 2 cosine of x sine of x. And then I would just divide both sides by whatever's in front of dy dx. So 2 sine of y cosine of y on both sides. Now, a common mistake is that kids want to cancel out cosine and sine. Cosine of x and cosine of y are not the same thing. So we can't cancel those out, but we can cancel these 2's out, and we can cancel out everything on this side. So my answer for dy dx should be cosine of x sine of x divided by cosine of y sine of y. So again, when you use implicit differentiation, just take the derivative of everything, but pay attention to what variable you're taking the derivative with respect to. Okay, let's do some whiteboard practice. So go ahead and hit pause, try to find dy dx for each of these examples. All right, let's see how you guys did. So on this first one, the derivative of x is just 1, dx dx goes away. Derivative of sine of y is cosine of y dy dx, so you divide both sides by cosine. Technically this is fine, but this would likely be on the multiple choice portion, and they probably would have converted 1 over cosine to secant of y. So either of those is okay. Over here, derivative of 2y is 2y prime, or 2 dy dx. X squared turns into 2x, I don't need the dx dx, and then sine y turns into cosine y dy dx, just like it did up here. Since I have dy dx on both sides, I need to subtract that term over, pull the dy dx out front, and then divide by that. All right. Now, on a problem like this, find dy dx for x to the power of x. And we're going to assume that we're thinking about something like y equals x to the power of x. This problem should say for y equals x to the power of x, so sorry about that. Also, let's change colors because this blue isn't showing up very well. So y equals x to the power of x. And this goes back to the topic we learned in this unit with the technique of logs. So when the base and the exponent both have a variable in them, that's when you should be using the technique of logs. So I cannot use any of the other rules. I'm going to need to take the natural log on both sides. And then now that I have a log on the right side, I can move the exponent in front. So ln of y equals x times ln of x. On the left side, I'm just going to get 1 over y times y prime. Y prime and dy dx are the same thing. On this side, I would have x times 1 over x, the derivative of ln of x, plus 1 times ln of x. Derivative of x is 1 times ln of x. All right, over here, these x's could cancel, so I'd have 1 over y times y prime equals 1 plus ln of x. To get y prime by itself, multiply both sides by y. So y prime would be y times 1 plus ln of x. And then you would likely see the y plugged back in. So dy dx is x to the power of x times 1 plus ln of x. Not sure where that line came from. Sorry about that. So the technique of logs is really just a way to use implicit differentiation, or that's where like implicit differentiation would pop up in the log problems. So this is just a review of the stuff we did on day 8.2. So if this doesn't make sense, go back and watch the 8.2 videos again. All right, let's see one more example, and then you guys will do some whiteboards. So find dy dx, and again, this should say y equals cosine of x to the power of x, so I apologize for that. And again, we would rewrite this as cosine of x to the power of x. Since the base and the exponent both have a variable in them, we have to use the technique of logs. So ln of y equals ln of cosine of x to the power of x. And the reason we do this is so we can get this x out of the exponent and move it in front. So ln of y is x times ln of cosine of x. On the left side, we just use the derivative of ln property, so 1 over y times y prime. On the right side, we're going to have to use the product rule. So x and then the derivative of ln of cosine is going to be 1 over cosine of x times the derivative of cosine, which is negative sine of x, plus the derivative of x is 1 times ln of cosine of x. So let's see if we can simplify this at all. 1 over y times y prime. Negative sine over cosine. I'm going to move the negative out front. So negative x. Sine over cosine is tangent. So negative x tangent of x plus ln of cosine of x. And then I would just multiply by y. So my final answer for y prime or dy dx would be cosine of x to the power of x times this thing. Now I'm running out of room, so I'm going to rewrite the whole thing. Let's try that again. So my final answer would be dy dx equals my y, once I multiply it over, so cosine of x to the power of x times negative x tangent of x plus ln of cosine of x. All right, now let's try a couple of whiteboard problems on this. And again, if I went kind of quickly, go back and watch the videos on 8.2 on the technique of logs. That's what we're doing here. All right, so go ahead and hit pause, see how you do. All right, let's see how you guys did. This first one, you do need to use the technique of logs. The second one, you don't, because e is not a variable. So the base is a constant, which means you can just use the exponential rule over here. So you have to use the product rule on cosine times sine, but you don't need to use the technique of logs. You can, but I think it ends up making it harder than it needs to be. Over here, you would want to use technique of logs because the base has the variable and the exponent has the variable. There's a lot of ln's to keep track of, so move the x in front, product rule. So here is probably the trickiest part for most students. I did x times and then the derivative of ln of 1 plus ln of x. So 1 over 1 plus ln of x times the derivative of 1 plus ln of x. So if I started with 1 plus ln of x, the derivative would be 1 over x because the constant goes away. So this part is probably the most challenging for most students. All right, hope this was helpful. Again, if you don't remember implicit differentiation at all, go back to Unit 4. The 4.1 videos are on basic implicit differentiation. And then after that, we got into problems that had related rates, which is what we'll do in the next couple of videos. All right, good luck.